Hello, everyone. Welcome back. Today, we're going to be talking again about alkyne reactions. But this time, we're going to be talking about hydration primarily. Because when we look at hydration of alkynes, it's a little different from what we saw in alkenes, right? So let's think about our classic alkene hydration. Right, let's just say that there's no special thing that I want to do here. We just choose this alkene right here, and we say we run a hydration on it. Every time we do this, we are going to end up in a situation where we have an alcohol, right? So we always go from our alkene to our alcohol. Now let's say we try and do the same thing, but on an alkyne, right? If we try and do a hydration of this alkyne, we don't just end up with an alcohol, right? We end up in a situation where there's now an alkene by this alcohol. And now, if you were studying your functional groups earlier in the semester, you might actually recognize this functional group as not being an alcohol, but rather this right here is called an enol. And the thing is, enols are very special because unlike a classical alcohol, that alkene is in resonance with the enol, right? If we think about resonance structures of enols, we see that from this enol itself, we can actually draw a resonance form where the oxygen donates some electrons down to form a double bond, and then it pushes the electrons from this double bond right here to form a negative charge on this carbon. And now this right here is a relatively decent resonance form, but it shows something very interesting, right? And that is the case. Sorry, I forgot positive charge right there. That is the case that it looks like you can form a carbonyl here, right? Because this carbon-oxygen double bond is essentially just that, a carbonyl. And funny enough, enols do end up showing a property like this. It is through this thing that we call ketoenol tautomerization. The idea behind this ketoenol tautomerization is that if we have an enol, right, and we're actually going to make this hydrogen very obvious, we're going to put it in blue. This can actually interconvert in equilibrium with its ketone counterpart, which has the same hydrogen, but moved to where that resonance structure showed that negative charge. And so this equilibrium exists between our enol and ketone. The question is just which one is favored. Well, if we were to do this based on classical delta H, and we were to look at our bonds broken, using BDEs, we would say that we've broken an OH, right, which is 102 kcals per mole, and we've broken a carbon-carbon double bond, which we know is not super strong, but it's sitting at about 65 kcals per mole. On the other hand, our bonds formed would be we've actually now formed a carbon-hydrogen bond in the products, right? And those are at 95 kcals per mole, while we're forming also the carbon-oxygen double bond, which is much stronger than the CC double bond at 85 kcals per mole. All right. So our delta H of this reaction, as shown swapping between the enol and the ketone, is about negative 13 kilocalories per mole. This is a favorable delta H. So what we can say here is that ketones are more thermodynamically favorable than enols. So this entire idea is tautomerization, right? And what this is based off of is the idea that enols and ketones are tautomers, right? And what a tautomer is essentially tautomers are constitutional isomers that differ only by the placement of a single atom. And that's why I highlighted that hydrogen. Because notice how all of the carbons stay in the same place, the oxygen stays in the same place. The only thing that moves is that blue hydrogen. In one case, it's on the oxygen, in the other, it's on a carbon. And the process of moving between these is what we call tautomerization, right? That is the chemical reaction that leads to a tautomer from another. So, this tautomerization, we can see, is favored from the enol to the ketone. But it doesn't just happen on its own, right? It's not possible for it to just go. Instead, it needs to be catalyzed, otherwise the reaction is going to be far too slow. And there's two ways to do this, and we're going to show both of them. So we'll start out with the acid catalyzed tautomerization. So, what does this look like? Well, the way this works is we can say if we start out with an enol, such as the one that we've been focusing on, and then we add in acid and water, we should be able to make the corresponding ketone, right? So just like H2SO4 and H2O should give us the ketone. The question just becomes, how does it happen? Well, to figure that out, we can draw out a mechanism. So, thinking about this, we already know that the first thing that's going to happen is we're going to form H3O plus in solution because we're mixing H2SO4 and water. And so with that, we have H3O plus that's going to act as our acid. So what happens from here? Well, from here, whenever we think about what is basic or nucleophilic in the molecule, we have an alkene. And this alkene's not just any normal alkene. There's actually resonance donation from the oxygen that makes it a better, more electron-rich alkene. So it's a really good nucleophile. So what it's going to do is it's going to come in and it is going to grab that proton just as it does every single time, right, as a nucleophile. And then we're giving the electrons to that oxygen to make it no longer positively charged. From here, we now have generated a carbocation, right? And it's going to be on this side here with this oxygen because this is the more stable carbocation. And it's not just due to substitution. Instead, if you think about this oxygen as having electrons that can be donated, we can draw a resonance form in which, as we described very early on in the semester, we can fill all of the octets that are on that carbon, right? So that carbon having an octet, it's now very happy, and the oxygen has a positive charge, which it doesn't like, but all octets are filled. This, of course, is a favorable resonance form. And what that means is that now this oxygen with its proton is now very acidic, right? That proton, if removed, will take that oxygen and make it neutral again. And so that's exactly what we can do. We can remove that proton, which makes it that neutral oxygen, and it is now the ketone. So this acid catalyzed tautomerization is actually a mechanism that you could have drawn a long time ago, because essentially it's two steps. Right? The first step is very simple. It is a protonation, right? We are adding a proton from the H3O plus to the alkene, to that carbon. And then the second step, right, ignoring the resonance and just knowing that happens, is a deprotonation, right? We're deprotonating the acidic oxygen. So overall, this is just Bronsted acid-base chemistry. So we could have talked about this mechanism all the way back with acid-base chemistry, but of course we needed a little bit more information to actually be able to fully do it. So that's the acid catalyzed route, right? Sulfuric acid and water will get you from the enol to the ketone, but what about the base catalyzed tautomerization? Well, in the case of the base catalyzed tautomerization, what we're going to see instead of using H2SO4 and water is we can get the exact same reaction to occur if we use sodium hydroxide and water, right? That will end up making our ketone. But you can imagine this mechanism is going to be slightly different from what we saw in the previous. In the case of this mechanism, unlike the acid, we can't use the alkene as an or as a nucleophile to attack an electrophile. Instead, we have this very basic hydroxide that can come in and grab the most acidic proton, which happens to be on our enol alcohol. At this point, we now have the oxygen with a negative charge. One may say that this oxygen is pretty good at getting rid of electrons, but in reality, all of these electrons are going to get tied up in resonance. Because if we do so, this resonance form that we can draw over here has the oxygen with a double bond to the carbon, which, as we know, is a stronger bond than the CC double bond by 20 kcals per mole. So this resonance happens because that CO is stronger than that CC double bond. So from here, what we see is that our water that we've generated from deprotonation from our hydroxide is going to act as the acid that this can then grab a proton from, and we end up with our ketone as the final product. And so notice that the difference between the acid and base catalyzed tautomerization is just the steps in the order they occur. Because the base catalyzed tautomerization is the same way. It's two steps, where the first one is deprotonation of the enol, and then the second one is protonation of the basic carbon, which notice is the opposite of our two steps from before, which were protonation and then deprotonation. Either way, both of them get you to the same product. The question is just which one is actually operant in the mechanism that you're looking at. All right. So now that we understand this idea, we can say that hydrations do not generate just these enols. Instead, it generates ketones through these tautomerizations. But now we need to talk about how alkynes are hydrated, right? So let's think about the general hydration of an alkyne. Back whenever we were looking at alkenes, we said that if you take them and run them with H2SO4 and water, that you would get hydration to occur. But if you do that with an alkyne, what you actually see is that there's no reaction. And this is a little weird because you may think, why would this be the case? Because if it happens with alkenes, why wouldn't it happen with alkynes? And think back to what we talked about last lecture when we were looking at the alkyne and alkene reaction rates in terms of doing these additions. These alkynes are much, much slower. Now, that being said, we saw previously in our other lecture that addition of HBr works just fine, right? You can add in a hydrogen that way, and then you're left with your bromide that can then go do what it needs to do. But here's the thing, whenever you do this reaction, right, what are you doing? You're interacting directly with the HBr. However, whenever we're doing this same type of reaction with H2SO4 and water, we're not interacting with the H2SO4. Instead, we're interacting with H3O plus, hydronium. And if we're interacting with hydronium, this is actually a massive difference because the pKa of HBr is right around -5, whereas our pKa of hydronium is right around 0. So in reality, the difference between these two is the rate, where this reaction here on the bottom is 10 to the fifth times slower than the HBr addition, right? And that 10 to the fifth is quite a large difference, okay? Because we have to remember for that HBr addition, it's already slow for alkynes. So in reality, we can't really use this H2SO4 water approach to do any of these reactions. Instead, we need to use other methods that don't generate this super unstable carbocation. And so what are those other hydration methods? Well, they're actually going to be the same ones that we saw from our alkene chemistry, right? Because think about it, that wasn't the only way that we hydrated alkenes. Instead, one really good way was one that we learned that was a Markovnikov hydration, where we use this mercury with water, followed up by sodium borohydride to add an alcohol, Markovnikov. Right? As a reminder, this reaction was called oxymercuration reduction. And this, of course, did give us that Markovnikov addition. But this also wasn't the only reaction that we used. Instead, there was another one where we took the alkene, reacted it with BH3, right, that borane, and then we used H2O2 and sodium hydroxide to end up giving us this anti-Markovnikov addition of the alcohol. As a reminder, this reaction was hydroboration oxidation, right? And this did an anti-Markovnikov addition of the alcohol. And what did these two things share in common? Well, the common linker between these is that neither generated carbocations. So what that means is that these should also work for our alkynes. Okay? So let's take a look at what these actually do for our alkynes, starting with our oxymercuration reduction. Well, in terms of if we take an alkyne and run it through this, our reagents are actually slightly different when we run it with an alkyne. Because again, we need this to react, but it reacts very slowly. So instead of what we used last time with those two steps, what we do is we actually use H2SO4, mercury sulfate now, HgSO4, and water, and we end up forming a ketone. So, how does this work? Well, we're actually only going to give a partial mechanism. Because the important thing about this is, and I'll write it up here, that we actually don't need to know what the mercury step does, just need to know the tautomerization. All right, so just like we saw in the other oxymercuration reduction, we don't need to know the entire mechanism for the exam. So what does the mercury do? Well, essentially, whenever you have that HgSO4 and water, what it'll do is it'll end up generating your enol, where the enol is now on the more substituted side of the alkyne. From here, this is when the H3O plus comes in, and we do generate the ketone. Of course, this second step here, all it is an acid catalyzed tautomerization. And like I said, you do need to actually understand the mechanism behind this step. All right. So as a reminder of what this would look like for this specific compound, we have our enol, and we're actually going to do this in such a way that we make it a little easier on ourselves in terms of steps. So the first step is still going to be the same, right? Where we have our H3O plus coming in and getting protonated or protonating the alkene. This, of course, generates our carbocation, where now our enol can get deprotonated. But again, we're going to show it a little quicker to where now this time, when we deprotonate this, it's more like an E1, where instead of having to show the resonance and the deprotonation, we show them all in one step. So that is how we do that tautomerization to get from the enol to the ketone. All right. And that's the entire point of this reaction. The first step gives us the enol, right, which we don't have to show the mechanism for. You don't need to know it for your exam. But then the second step is that acid catalyzed tautomerization that you do need to know the mechanism for. A very similar trend happens with our hydroboration oxidation. But the difference here is that this one's actually the exact same as what we saw in the alkene reactions, right? And so what that's going to look like for us is that if our alkyne is subject to the exact same reaction conditions, BH3, and then that H2O2 and hydroxide, what we're actually going to see here is that we're going to end up making an aldehyde. Okay? So it's the same conditions and mechanism as alkenes. The only difference is the end of it, right? So we're going to do another quick partial mechanism here where we say, okay, well, in this first step, having BH3, we already know what's going to happen here. We're going to end up adding, in a syn fashion, the hydrogen and the BH2. From here, this is when our second step comes in, which is that H2O2 and NaOH. And at some point in this reaction, we end up with the alcohol, just like we saw with our alkenes. But in this case, rather than being an alcohol, it is, of course, an enol. And upon further reaction with the sodium hydroxide, that is what turns it into the aldehyde. Of course, this is, once again, a tautomerization. We're going from the enol to the carbonyl. And this one is a base catalyzed tautomerization. And once again, we do need to know the mechanism for this. So, the mechanism for this tautomerization is very simple. Starting from the enol, we have the acidic proton that's on there. And so our hydroxide comes in, grabs that proton, and forms the now enolate, right? So just a negatively charged oxygen on the enol. This can then get protonated by H2O acting as the acid. And for this one, we can also show the resonance and the acid base all in a single step. And so that's how we get to our aldehyde. So when we think about hydrations of alkynes, what we're essentially doing is we're following the exact same procedures as we did for alkenes, right? We're doing either Markovnikov or anti-Markovnikov addition of the alcohol. But of course, with the alkyne, that means it's going to be an enol. And then from there, it can then do a tautomerization to form whatever carbonyl we desire. And then the carbonyls are generally unreactive to further conditions in the reaction. Okay, so that is one of the major differences we see between alkyne and alkene reactions. Is it's not just they always react twice, sometimes they do weird side reactions. But one thing that can react twice is something like a halogenation reaction. So as a reminder, halogenation of alkenes is when you come in and you add in something like Br2, right? Now with alkynes, of course, we can actually do two different things. It's the same as we saw last lecture, where if we add one equivalent, we're going to get one thing, and if we add two equivalents, we're going to get something slightly different. So with one equivalent, we end up having our alkene, where we've now installed bromines, and they are actually anti to one another, right? So that just means that they're 180 degrees apart. With two equivalents, though, the alkene that we have now formed can undergo a second halogenation, and we essentially just get a huge number of bromines, or whatever halogen is that we're talking about, all over the structure. All right? So, looking at the mechanism behind this, this likely will not surprise you on how it works because it is the exact same as we saw for our other halogenation reaction, where if our alkyne comes in contact with bromine, just like in alkene chemistry, it will attack one of the bromines. That bromine will attack back and kick out the other bromide. Now, at this point in time, we have a very strained complex where we both have the alkene and the three-membered ring in the same structure. But it still reacts the same, right? Because this bromonium ion is essentially the same as like an acidic epoxide opening, where our bromide comes around and does a backside attack. And that is what generates our anti-stereochemistry, right? Where one bromine is going to be 180 degrees from the other. And so this structure here, this is where we stop if we have one equivalent. On the other hand, a second equivalent of bromine could be added, and this one's going to do the exact same thing, where it attacks, the bromine attacks back, and we kick out one of the bromides. That generates, whoops, no alkene anymore, a bromonium ion, which from that point, another equivalent of the bromide, which we just kicked out, is going to act as the nucleophile, come in, kick out that bromine, and we're going to end up with our racemic mixture of bromines all over. So, essentially, this is another one of those alkyne reactions that just do the same thing twice. Now, with all of this being said, there are no other reactions that you need to know from alkyne chemistry. There are a couple that we didn't look at here that just don't exist with alkynes, but they do with alkenes. Think things like syn dihydroxylations. They just don't exist. You can do things like epoxidations that get really janky, it doesn't really exist either. And then ozonolysis does exist, but we're not going to worry about it. So overall, this is the end of alkyne chemistry here. Now, that being said, one very important thing that I want to stress about alkynes is that most alkyne reactions end with racemic stereochemistry due to adding two of the same thing. Why does that matter? Well, because if you take a look at this final product that we formed down here, we have essentially made each of these carbons achiral because the two bromines are the exact same thing. Same thing with as we look up here with these tautomerizations, the C double bond O cannot be anything other than achiral. Now, that being said, the one difference between this is intermediates slash stopping at one equivalent can have stereochemistry. That being said, it's often similar to what we see in alkene reactions. So, overall, that's the end of alkenes and alkynes. Next lecture, we're going to be hopping into looking at how to use these reactions to gain further understanding of the entire landscape of organic chemistry. And then for the last couple of lectures, we're going to finish off talking about how we can combine all of the tools that we've been gathering throughout organic chemistry to do the one thing that organic chemists can do that everyone else is unable to, which is actually create and synthesize and use these ideas to make cool compounds that hopefully you all find enjoyable. So that being said, I'll see you next time to really wrap up alkenes and alkynes with a big picture overview. See you then.